Hey, AP Chem, welcome to Unit 3. We're going to cover chapters 4 and 11. We'll start in 4, and this whole chapter is applied chemistry into solutions. It's like the chemistry that happens in solutions. So in order to talk about this, we're going to start with a whole bunch of definitions. Some of these you may have heard before, and some of them may be new. So let's run through these definitions so that we can use them as we go through these chapters. Okay, so to start us out, we're going to talk about solvents, solutes, and aqueous solutions. So the solvent is the thing that's doing the dilution. Usually in our class, our solvent is going to be water. We dissolve things into water. So whatever the medium is that you're dissolving into, that's your solvent. The thing that's being dissolved is your solute. So if you're making sugar water, your sugar is your solute. Your water is your solvent. Now, anytime that your solvent is water, that's going to be an aqueous solution. And notice we have this little symbol there. So that symbol now is going to get added in when we're talking about something like NaCl. We can talk about it as if it's solid, which would be the crystal form. You can talk about it as if it's liquid. That would be the molten form. If you like melted sodium chloride so that it was flowing, picture lava. That would be liquid NaCl. You could have gaseous form. I don't know if that's actually possible with sodium chloride, but you get the idea. Now we have a fourth one, which is this aqueous form. So if NaCl is our solute and it's dissolved in water, we're going to list it as aqueous. And we do this because it doesn't nicely fit into any of these other three categories. When you dissolve sodium chloride into water, you have a liquid, but your sodium chloride isn't liquid. Your sodium chloride is technically solid, but it's not a solid crystal. The Na and the Cl break off from each other, and they're floating around in the liquid separate from each other. They are not currently in their lattice. So because it's this unique state, we have an entire label for it. And so this whole section of what is the chemistry that happens in solutions, we're going to be dealing with this aqueous label a lot. One thing to remember when you're dealing with a solution, remember, a solution's a mixture, right? If we have aqueous NaCl, if we've taken NaCl and dissolved it into water, we have two pure things that are mixed together. They are not bonded together. They haven't taken on a unique identity. They are still both present. They are still both expressing their unique identities. And so you have a mixture. When you're talking about you have a mixture, you do not have a pure substance. So that's one of the things to kind of differentiate between is mixture versus a pure substance. So mixtures and substances are different. Also, it is a homogeneous mixture. If you have a solution, you are talking about a homogeneous mixture. So this prefix here means same. If you had a mixture where you could see the different parts in it, that would be a heterogeneous mixture. Hetero meaning different, right? A homogeneous mixture means that every sample of the solution looks exactly the same. Every sample of the solution has the exact same chemical composition, has the exact same ratio of sodium chloride to water. That is a homogeneous mixture, and that's what we call a solution. Now, how can you be, you ask, right? If we take red Legos and mix them into blue Legos, a whole bucket of blue Legos, those red Legos aren't going to distribute themselves evenly, right? Because there's no attraction between the red Lego and the blue Lego. Why would they distribute themselves equally? They wouldn't, right? But NaCl and water do have attractions between them. And because of those attractions, not bonds, attractions, the Na plus, the Cl minus, and the H2O are going to distribute themselves evenly, and we get a solution. So it's a very specific thing that we're talking about with actual definitions. We throw the term around in society, but in chemistry, we're talking about something very, very specific and well defined. So let's take a look at what those attractions are. All right, so before we talk about the attraction in the solution as a whole, you have to know a little bit about the properties of water. So we haven't talked about bonding and molecule shapes yet, but I think we can talk specifically about those things in water and kind of move forward with that definition. And once we get to bonding and intermolecular forces, then we'll talk about these for all molecules as a whole. But right now, let's really zero in with water. So when you are talking about water, H2O, right, we're talking about something that is covalent. So the hydrogen is bonded to the oxygen, is bonded to the hydrogen. This is what your Lewis structure would look like. Notice that these electrons here are being shared, right? They spend some time around the oxygen, they spend some time around hydrogen, but they're not pulled off the hydrogen onto oxygen. We don't have complete charges inside this molecule. It's a covalent molecule, right? However, they don't have equal electronegativity. So looking at this molecule, which atom inside the molecule would have a greater electronegativity? Would that be oxygen or hydrogen? I'll give you 5 seconds to answer. Oxygen, right? Oxygen is going to be much more highly electronegative. It's going to have a much higher attraction for the electron than hydrogen is. So although these two electrons here are shared between hydrogen and oxygen, it doesn't mean that they spend equal amounts of time among both atoms, right? These are actually pulled towards oxygen because oxygen is more electronegative. So these electrons that are bonding hydrogen to oxygen, they spend more time around oxygen. They spend a little bit less time around hydrogen. And that means that oxygen is going to be partially negative, not a complete charge, but a partial charge. Hydrogen, because the electrons are pulled away from them because of their low electronegativity, hydrogen is going to be partially positive, right? Both hydrogens, partially positive. Okay, in addition to this, water is also a bent molecule. And when we get into bonding, like I said before, we'll talk about why. Why is water a bent molecule? We'll talk about that later. For now, just trust me, water is bent. You can see the shape here. Okay, it's not linear, it's bent. It's bent at a 104.9 degree angle. And so these charges here, they act like vectors. If you've ever done any vector math, either in physics or in one of your math classes, you know that if vectors are equal and opposite, they're going to cancel each other out. They're going to reduce each other out, right? You can think of a tug of war. If we have vectors that are opposite and equal, they're going to pull in opposite and equal directions, and they're not going to move the center of that rope, right? But not so if your ropes are bent. If your ropes are bent and they pull in that bent direction, the center of your rope is going to move, right? They're not going to cancel each other out or reduce each other out. And that happens in this molecule also. We have these two vectors that are equal, but they're not opposite. They're not going to cancel each other out. And so what you get is an overall movement of the electron. And you can see this in this molecule. You can see the red side over here. This is where, notice that it's bigger than the green side over here. And it is showing you the electron distribution cloud. So where do the electrons spend their time? Well, they spend more of their time over here by the oxygen, and they spend less of their time over here by the hydrogen. Also, that's what the red color is supposed to indicate too. Red is supposed to indicate a higher presence of electrons. Green is supposed to indicate a lower presence of electrons. So you can see that this cloud gets shifted because of oxygen's what? High electronegativity, right? All right, so electrons get shifted inside the bonds, and because the bonds are bent, that electron shift doesn't cancel itself out. It ends up having a charge. It ends up having like a net pull in one direction. And we have this side of the molecule that ends up partially negative. This side of the molecule, these sides of the molecule end up partially positive. This is what we call a polar molecule. A polar molecule has partial charges. It is different than an ionic molecule, which has actual charges. The electron actually gets transferred, and you have complete charges and occurring at each end of the molecule. Well, here we have partial charges that occur in different parts of the molecule. Now, these partial charges, they still have an effect similar to actual charges. And so these partial charges can attract things. This partial negative charge can attract positive things. This partial positive charge can attract negative things. And so as a result, water, which is highly polar and small, can dissolve things that are charged because water is polar. If water wasn't polar, it wouldn't be able to dissolve charged things. It wouldn't be able to attract charges. But because water is polar, it can attract charges. It can dissolve charged things or partially charged things. All right, so here we see in this little picture right here we see water molecules that are being attracted to something. So take a look at this picture and see if you can figure out what that green thing is. Based on how the waters orient around it, what is that green thing? I'll give you 5 seconds to think about that. Okay, so you see that the white part of the molecule, and remember that white part is going to be the hydrogen, that's your partially positive part. Those are all attracted to this green thing, and so this green thing must be negative because the partially positive end of water is attracted to it. Okay, so this is a beautiful picture of something called hydration. If we talk about hydration, what you are describing is these charged particles or partially charged particles that are dissolving into or attracting water. Now, you can hydrate something by dissolving it into water. Something can also hydrate by absorbing water out of the atmosphere. And we talked about this before with copper 2 chloride, right? We can have anhydrous copper 2 chloride, and that would be copper 2 chloride that is dried. All the water has been driven off of it. Or you can have copper 2 chloride hydrate. So for every 1 copper chloride ratio, 6 waters get stuck in that crystal. And this anhydrous copper 2 chloride is going to be white and powdery. And this hydrated copper 2 chloride is going to be blue and beautiful and gem-like. it looks like, if you can get the crystals big enough, it looks like this big blue sapphire, which it's not because you can crush it, and also dissolve it. But it's really pretty. It actually turns color, and it turns into a specific shape if the crystals are given that opportunity to form on each other. So it's pretty cool. So this term is going to be thrown around. Here you can see it used in a sentence. The salt is hydrated. Same idea. We can write the hydration reaction of a salt. Here you see the hydration reaction of NaCl. We can, if we were to throw in states there, these would be the states. Notice that water is listed above the arrow. So it's not technically part of this reaction, but it is listed above the arrow to show that it is involved. So now would be a really good time to pause and try to write your own hydration representation of this molecule. It would also be good practice if you tried to name that molecule. Okay, so pause it and try. And I'll do the same. This is ammonium pernitrate. Oh, and these could both get aqueous written behind them. Okay, now notice that the two practices that we've done so far, sodium chloride and ammonium pernitrate, have both come out to be a 1:1:1 ratio. That's not always true. If we do the same thing for copper 2 chloride, for example, CuCl2, if we start it as a solid, we're going to hydrate it with water. It will end up in Cu2 plus and 2Cl minus. And notice that that ratio is a 1:1:2 ratio. So you do have to pay attention to how many ions are in your salt. And if there's more than one in your salt, notice that it's going to turn into a coefficient and not be stuck as a subscript when you pull the crystal apart. There's 2 chlorine ions inside that compound. That is not diatomic chlorine in that compound, right? So make sure you can specify that difference. Okay, when we are describing salts and dissolving salts into water, there are differences in solubilities. So sodium chloride is considered a highly soluble salt. Silver chloride is considered a slightly soluble salt. And there are other salts that are considered to be non-soluble salts as well. Okay, so now it's really, really difficult to predict what kind of salts are going to be highly soluble, slightly soluble, or non-soluble salts. If you are looking at a molecule or you're looking at a periodic table, the interactions are just too complicated in order to make a prediction as to what kind of a salt it's going to be. The difference depends on the size of the ions, how attracted the ions are for each other, and how attracted the ions are to water. So you can think of it as a balance. If I tell you that something is highly soluble, then you should be able to tell me if it has a higher attraction for water or for each other, right? If it has a really high attraction, if the ions have a very high attraction for each other, it's going to be non-soluble. if they are more attracted to each other than they are to water, it'll be a non-soluble salt or a slightly soluble salt. If the ions have a high degree of attraction to water, they're more attracted to water than they are to each other, it'll be a highly soluble salt. So it has to do with this balance between attraction. Super hard to predict. But if I tell you if it's highly, slightly, or non, you should be able to rank those attractions for me. Once these things are hydrated, the ions are going to move apart independently from one another. So if you put NaCl into a beaker full of water, you'll get Na plus ions and Cl minus ions that are surrounded by little water molecules, right? And these water molecules form kind of like a little shell around these ions. And so they don't really, the Na plus and the Cl minus are protected by water, and they don't interact. There's no interaction with each other anymore. And so they can kind of freely move about this solution with no respect for each other's location anymore until you start to remove the water through like evaporation or maybe distillation. And once enough water is pulled off of these ions, then they start to reform into the crystals together. But that only happens once the water is removed. As long as the water is there, they're not going to be attracted to each other. Okay, so when we're talking about polar molecules, here's the phrase you want: like dissolves like. So polar molecules are going to be attracted to other polar or charged molecules. If it has a partial or a complete charge, it's going to be attracted to something else that has a partial or a complete charge. If you have a non-polar molecule, it's going to be attracted to other non-polar molecules. So think about this in your kind of day-to-day life. What kind of things can you put in water that will dissolve? What kind of things can you put in water that will not dissolve? And some things that I can think of that would dissolve in water would be something like sugar, which is a polar molecule, salt, which has charges, it's ionic, has charges inside the molecule. Things that won't dissolve in water would be something like butter. Butter is this super long chain of carbon atoms, carbons and hydrogens, super, super, super long chains of carbons and hydrogens, like longer than our whole page. If we were to draw them out, I mean, hundreds, maybe thousands of carbons and hydrogens, right? So things like this are not going to be very polar. They're not going to tend to have charges. The carbons and the hydrogens have really similar electronegativities. And even if they do have charges, they're so spread out over this super long chain that the charges are kind of like dismissed or dampened, right? So butters and oils tend to be non-polar molecules, and they'll dissolve each other, but they won't dissolve in something that's polar, like water, which is why you get that little layered effect. If you put oil and water together, they separate out into layers. Okay, another way to describe solutions is through electrical conductivity. So as we're analyzing solutions and we're trying to figure out what's in our solutions, one of the ways we can analyze it is through electrical conductivity. And so in this, we need to do a couple definitions again. So first of all, if something conducts electricity, basically what you have is little charged electrons that are jumping from thing to thing to thing to thing to thing in your solution. Electrons have to have some type of charge inside the solution that they can jump from and to. And if there's no charge inside the solutions, the electrons have nothing to jump and connect to, and the electrons cannot move through it. So if electrons can move through your solutions, we say that the solution conducts electricity. If electrons cannot move through the solution, there's nothing in your solution that can support these electrons, then we say the solution does not conduct electricity. And the way that we check this is by taking our solution and putting in leads that are connected to some type of battery, and that battery is connected to some sort of a light source, usually an LED light source, because it doesn't take a whole lot to light an LED light source up. So if the solution can allow these little electrons, there are little electrons. The battery is pushing little electrons through the wire. When the little electrons are pushed into our light bulb, the light bulb filament glows, right? Until our electrons get to our solution. So what happens is if the electrons can jump from one thing to another thing in our solution, then the electrons will keep getting pushed through this wire by the battery, and the light bulb will stay on. If there is nothing in our solution to support those electrons jumping or moving, then even though the battery pushes, the electrons can't get past our solution, and the light gets turned off. So what we're checking for is if the light is on, then you have ions present because you have something there that will support the movement of the electrons. If the light bulb is off, that means there's no ions inside your solution to support that movement of the electrons. And so what we call these ions when we're checking for conductivity, we call these ions electrolytes. And that's exactly what electrolytes are. If you are working out really hard and sweating a lot and you're not drinking enough fluid, what you're going to do is you're going to sweat out all your electrolytes, and then you have no more electrolytes inside your body to support the making of energy, the processing of energy. You need electrolytes in your body to support the energy making process. Well, guess what these electrolytes are? They're ions. They're things like potassium and sodium. And so when you get a sports drink and they're like, oh, we'll replace your electrolytes, right? All they have inside, they have potassium chloride dissolved inside. They have sodium chloride dissolved inside. If you look at what your electrolytes, if you look at the label on your bottle of your sports drink, it'll tell you exactly what your electrolytes are. Just look for the salts. Whatever salt you see, those are the electrolytes that they're trying to put back into your body so that your energy process can go on. Now, usually if you drink a bottle of Gatorade, you have replaced your electrolytes by like 100-fold. You definitely don't need that many electrolytes in your body, but it tastes better, right? When the electrolytes are concentrated. And so that's why they put that much in to your Gatorade, right? Okay, so ions and electrolytes, those are the same thing. When we say that a solution is a strong electrolyte, it means it has a lot of ions that are present. Let me erase this and I can write a little bit more. So strong electrolytes would have a lot of ions present, which means that whatever salt you have dissociates completely, and all the ions that were locked up in that original crystal or lattice are now released and free to flow throughout the solution. So you would have a lot of strong electrolyte means you have a lot of ions present, which means your salt is soluble. And the light is going to turn on really bright. If you have a weak electrolyte, that means that you have a few ions present. The light is going to be kind of dim. You have some electrons that can get pushed through there, but not a whole lot. An example of that would be a salt that is slightly soluble. And an example of that would be acetic acid. We'll talk about weak acids and strong acids here in a little bit. Non-electrolytes would have a light that is unlit, and this means that there are no ions present. Even if your thing dissolves in water, that would mean your thing is polar, right? Well, polar things don't fall apart into ions. They just stay as their own little polar molecules, like sugar. So you would have a non-electrolyte would have no ions present, which means either you have an insoluble salt or you have a polar covalent molecule, not an ionic molecule. Okay, so those are your categories. Now, we're going to get into acids and bases in a little bit here. So when we get into acids and bases, listen for what categories those acids and bases get put into in the strong, weak, non-electrolyte. So this is a test you can do on your solution to see what is in my solution.